Welcome back. We're going to talk about water chemistry today. Basically, what I mean by that is we're going to talk about the properties of water and why that's so important to life. And I know this seems kind of like a stupid topic to talk about, but the chemistry of water is actually quite fascinating. And to see how its polarity can create so many different emergent properties is just so cool. And to see it interplay with life is a lot of fun. So let's dive in. These are the key terms for this specific lesson, and let's dive in. So we mentioned this in the last video, but water's polarity is going to directly cause all of the other properties that we're going to talk about today. Its polarity is the most important thing about it. And remember that polarity is when a covalent bond shares its electrons unequally because one of the molecules is going to crave those electrons a little bit harder. It's going to be what we call electronegative, more electronegative. So in the case of water, the hydrogen and the oxygen share an electron pair, but the oxygen is going to hog and hold on to those electrons a little bit more often than the hydrogen will. They're shared, but just not equally. The electrons don't spend quite as much time or aren't as close to the hydrogen as they are to the oxygen. So as a result, the oxygen has a partially negative charge to it, and the hydrogens will have partially positive charges to it. Water overall is not a charged molecule. It is neutral. However, it has areas that get partial charges throughout its existence. Now, that's a key thing to remember, that this is not an ion. It's not a true positive and a true negative. It's just a partial association. Now, because of polarity, remember we can form hydrogen bonds. And this is really where a lot of the magic is going to come in when we talk about water too. So hydrogen bonds are not true bonds. They're interactions where the partially positive region of one polar molecule is going to be attracted to the partially negative region of a different water molecule. So as a result, these two different molecules or compounds are going to be drawn together. Think of it like a magnet. It's not truly a magnetic force, but that's the best example I can relate it to. Two magnets come together, they're still two magnets. They're just kind of associated and attracted to each other. They don't meld together and become a big magnet. They don't meld together and become something entirely new. We're not undergoing a chemical reaction and change. We're just kind of being attracted to each other here. So it's an attractive force, not a bond. Now, that polarity and those hydrogen bonds create all these other properties that we're going to talk about today: cohesion, adhesion, capillary action, high specific heat capacity, and the fact that water is a universal solvent. And without all of these things, it's hard to believe, but without all of them, life could not exist. We need water, and we need all of these different abilities of the water for even our biology to function properly. So the property of cohesion is what occurs when water forms hydrogen bonds only to other water molecules. So they're only forming these between each other, kind of like that picture on a couple slides ago that I showed you, where the partially negative oxygen is hydrogen bonding to the partially positive hydrogen of a different water molecule. So there's an emergent property that comes out of this, and that is surface tension. So at the surface of water, water forms some extra cohesive bonds, some extra hydrogen bonds, and this creates a really strong layer of multiple atoms at the top that's hard to break. It creates that strong tension. If you ever like balance your hand on the top of water, if you go swimming, it almost feels like you're pushing up against a film and you have to push to get past that slightly. This is the emergent property that allows water to form droplets. And the more important thing is this is one of the properties that allows water to form pools, not like swimming pools, but like puddles and ponds and things like that. And it allows these little tiny bodies of water to persist for a longer amount of time because the solar energy, the radiation from the sun and the heat from the sun is got to work a little bit harder to break all those hydrogen bonds before all that water evaporates. So it allows that water in the little pond, in the little pool to persist and allow little life to be able to take advantage of it. Adhesion is a similar concept, but it's when water forms hydrogen bonds to other types of polar or charged molecules, not to water. So cohesion was water to water. Adhesion is when water bonds to something else, like in this case, ammonia. The nitrogen is kind of similar to the oxygen in water where it wants to hog all the electrons. So the hydrogens become partially positive and the nitrogen becomes partially negative, and we can then form a hydrogen bond between water and the ammonia. So this is the property that makes water stick to other surfaces. And this is great for organisms in arid or dry environments because often the water will condense as it goes from evening to morning. It'll condense onto their body and stay stuck to them. And so they're able to then collect that water and drink it, even though there's not a lot of water available in pools and ponds in these dry desert areas. The next one is kind of a really cool emergent property when we put cohesion and adhesion together. And it's called capillary action. So a capillary is just a really, really tiny, thin tube. And so capillary action is a very cool phenomenon where water is actually drawn up the tube without the application of any external suction or the presence of a vacuum or anything like that. So there's nothing drawing the water up actively. The water is climbing up effectively, passively in this case. And the smaller the tube, the higher the water is able to climb. So what's happening is adhesion is causing the water molecules to stick to the inside walls of this tiny tube. And the cohesion is strong enough to kind of drag the water up the sides. And so water can climb until the overall effect of gravity is stronger than the effect of the forces of adhesion and cohesion. Only then will the water stop to climb up the tube. So overall, these passive forces that just occur because of positive and negative interactions allow the water to climb up the tube as far as they possibly can till gravity starts to take over and say that's far enough. So nothing is putting an external force. There's no energy applied to this. It's completely passive, which is cool. And that's important because this phenomenon is crucial for plants to be able to pull water out of the ground and into their roots. If you've ever looked at a root and you try to keep it as intact as possible, you'll notice that roots look hairy. And those little hairs actually have little tiny cellular hairs on them too. And they're these really, really tiny cellular tubes that suck water out of the soil passively using capillary action. And this allows plants to take as much water out of the soil as possible and get them out of the roots and up into the trunk where there's other types of forces that then are at work that draw the water up the whole plant itself. But capillary action is really important for that survival of those plants. The next really cool property and characteristic of water that we're going to talk about is how water has a very high specific heat capacity. Now, if you've never taken chemistry, let me define this for you. It's basically the amount of energy required to raise the temperature of a material by 1 degree Celsius. Putting that in normal language, how much energy does a substance have to absorb before it changes any temperature? Now we can see on this table here, water's way down at the bottom. It has a very, very high specific heat capacity. whereas metals tend to have very low specific heat capacities. This is why it takes forever for your water to boil when you want to make pasta. But if you put a spoon inside that pot while you're boiling water, a metal spoon, you can't touch it within seconds because it's way too hot to touch. The metals change their temperature very quickly when you apply energy to them. Water, you have to apply tons of energy before it'll start to change its temperature. Well, why is that? Because of all the hydrogen bonds. So water is constantly hydrogen bonding to itself, and it has all that really strong surface tension. So in order for the molecules to move and vibrate faster, which is what temperature is, it's the change of speed of the molecules. In order for them to vibrate more freely and vibrate faster, they actually have to break those hydrogen bonds and disassociate from each other. So to break all of those associations, to pull those magnets apart, it takes an extra expenditure of energy. Now, this you might think is just annoying because in our daily life, all we really care about is making sure we can cook our top ramen as fast as we can. But in the end, this is actually really important for life because we're constantly having solar radiation input and the sun is really hot. And excuse me, if everything around us were to constantly switch and shift temperatures as quickly as metals do, life couldn't exist. Our molecules would be melting and then reforming and then freezing and then melting again, and it would just be too much. So by having our molecules in water, all of the things that we do, our cells are constantly bathed in water, it makes them fairly temperature regulated. We can be out in the sun and we won't get a big shift in our internal body temperature. Additionally, if you're near the coast, it's really apparent here where we live. If you are to drive into LA and go to Santa Monica, it might be really cold there. It might be, in the 60s, 70s, and yes, that's cold for us in California. But then come into the valley where our school is, and it might be 80, 90. And that is entirely because we have the body of water, the Pacific Ocean, kind of sucking that heat away from the land. So the further inland you go, the higher the temperatures tend to be. And we tend to have this nice temperature modulation no matter what the season is on the coast because we have that insulating effect from the water. The last thing really here that we're going to get into is the fact that water is a universal solvent. So a solvent is something that dissolves other things. The solute is the thing that gets dissolved, and together they make a solution. So sodium chloride, which is table salt, you put it into water, it dissolves, and you make a salt water solution. Water is the solvent, and the sodium chloride or salt is the solute. So water has a term, it's called the universal solvent, meaning it can dissolve most polar substances. Pretty much almost every polar substance, water can dissolve it. And the way it does this is by forming hydration spheres, and it all comes down to polarity and hydrogen bonding again. If the substance of the solute is polar, then water is going to try to form hydrogen bonds to it. And sodium chloride is it's not a polar molecule, it's a charged molecule because it breaks down into ions, the positive sodium ion and the negative chloride ion. So in this case, or chlorine ion, excuse me. So in this case, the positive hydrogens are going to want to completely surround the negative chlorine, and the negative oxygens are going to want to completely surround the positive sodium. We call these hydration spheres. And when the water does this, it'll actually pull little tiny ions away from the broader grouping of that molecule. And as it pulls them away, it dissolves it and it turns it into a solution. And eventually you have the whole thing covered in hydration spheres. And when that happens, the negative action of the chlorine ion cannot associate with the positive part of the sodium ion. And so they cannot reassociate to form salt again. They just get dissolved into their ions. So we call this an aqueous solution, where water is the thing creating the solution. Things are dissolved in water. And aqueous solutions are so important to living things. It's going to allow us to transport nutrients throughout our body because we often will dissolve the food that we eat into our bloodstream, and then we can send those nutrients that are dissolved into our blood all over our body to get to every single cell. Plants do this with tree sap and other types of sap-like liquids and latexes that they'll have in their veins. So this allows us to not only transport nutrients, but to do chemical reactions inside our cells at a much faster rate than normally we can. So it's really important that our cells are basically made of water because water is the universal solvent. Now, key thing is here that it can dissolve most polar substances. The polarity and the charge and the hydrogen bonding is what is causing this to occur. Water cannot dissolve nonpolar molecules. So anything charged or ionic with a distinct positive and negative charge, water can dissolve those because it's those positive negative associations in the hydrogen bond. Same thing with our polar molecules where we have that unequal charge distribution. But nonpolar molecules, there's no positive or negative anywhere. Everything is equally shared. So effectively, water looks at this and doesn't even see it. It's like it's invisible to water. So in this case, if the electrons are shared equally, water cannot dissolve it. If it's nonpolar, it cannot be dissolved by water. So this gives us the terms hydrophilic and hydrophobic. Compounds that are entirely nonpolar cannot hydrogen bond to water, cannot be associated or dissolved by it, so they are hydrophobic, afraid of water, like arachnophobia, you're afraid of spiders. Phobia means fear, hydro means water. We call molecules that are like this water repellent. So anything that you need to make as an engineer, that you need to make sure water does not get into your components, you often want to surround whatever the important part is with something that is hydrophobic or water repellent so water can't get in and start breaking it down. Anything polar or charged that can hydrogen bond and can be dissolved by water, we call that hydrophilic. So there's gradations of how hydrophilic or how hydrophobic things can be, but these two terms are going to come important later when we start talking about cells and how things move in and out of the cells. That's going to be really important because inside our cells is water, outside of our cells is water, but our cell membrane is a fat. And fats and waxes and oils, those are all nonpolar. That's why when you have a salad dressing, the vinegar, which is water-based, and the oil don't mix. And if you shake them up, you'll see little beads of oil in there. And if you leave it alone, they'll eventually separate because the oil, the waxes, the fats, those are hydrophobic. So that is it for this video. If you have any questions, please don't hesitate to reach out.